Humanity has always dreamed of defying aging, even reaching for immortality. From ancient myths of elixirs of life to modern quests for eternal youth, humanity has always dreamed of defying aging, even reaching for immortality. But what if in this age-old aspiration isn't just a dream but a rapidly approaching reality? What if we could not only extend our years but truly enhance our health span, the vibrant, active period of our lives? Today, we're diving into this groundbreaking question with Brad Thompson, a visionary leader from Wyvern Pharmaceuticals, who asserts that longevity is a solvable now. Brad is not just theorizing it, he's at the forefront of developing gene correction technologies that could fundamentally redefine how we age. And he has a very personal stake in this evolution. This conversation will unravel the science of aging, explore how we can reverse its effects, and paint a picture of a future where health and vitality are extended far beyond what we currently imagine. Welcome to the WATSNEX podcast, the show that explores the intersection of innovation, market strategy, and operational excellence in high-stakes industries like life sciences. I'm your host, Pascal, founder and CEO of WATSNEX Biopharma. With over 25 years of hands-on project management and leadership across the entire life sciences value chain, from R&D and regulatory to tech transfer, manufacturing, and commercialization at companies like Pfizer, Merck, Novartis, and Mediata, I've witnessed firsthand the profound impact of technology and cutting-edge AI-driven commercial acceleration strategies. Today, we are incredibly fortunate to welcome back Brad Thompson, Chairman, CEO, and CTO of Wyvern Pharmaceuticals. Brad recently joined us for a fascinating discussion on disrupting disease, Brad Thompson's vision for gene correction in new healthcare era, where we explored how gene therapy could address 90% of current medical spending. Today, we're taking an even deeper dive into a topic that he has profound personal and professional interests in, the science of forever, Brad Thompson's on gene correction, longevity, and the future of health. Brad, welcome back to the show.
Thanks, Pascal.
Brad, it's great to have you back. When we spoke last, you hinted at your personal interest in longevity, especially as you approach your 70th birthday. You even said that longevity is not a problem. Can you start by explaining the fundamental scientific basis for that bold statement? What is aging at the genetic and cellular level? And what are the key mechanisms like somatic mutations and epigenetic changes that drive this process?
There's been some very good work, not done by me, in the last few years about the relationship between somatic and epigenetic mutations or changes and lifespan. And I think it's pretty clear that it's like you're accumulating damage as you go along, and at some point you accumulate enough damage and then you die. In mammals, it looks like it's between 5,000 and 6,000 somatic mutations and about half of that epigenetic mutations that results in you having a very high probability of dying after you get that many. And with humans, that typically hits in your mid-80s from a genetic perspective. And of course, there's a broad band around that because the mutation rate is quite different in different individuals. But that is the kind of the limiting factor. And a friend of mine said to me, "Well, so it's like a car," and I'm like, "Well, kind of like a car because those all those mutations obviously don't affect lifespan. I mean, they don't. Some of them, however, will affect health span, which is different than lifespan, and some of them will affect basically cosmetic health, if you want to think of it that way. So, I mean, the car analogy works. If you scratch your car door, that's cosmetic health. That's not going to affect the operation of the vehicle, nor is it going to affect the lifespan of the vehicle. I mean, that works. And so, if you're talking things like, all of us get elastin and collagen down regulation, usually epigenetic changes as you age. And so, yes, that's of interest to me. It's and we've done both of those with gene vectors. We've restored elastin, native elastin levels to where you'd be when you were 20, if you want, and collagen the same too. So I mean, we can do that, but those mutations don't affect your lifespan. So it's a much smaller number than the say 7,500 to 9,000 range when you add the two of them together. It's probably under 100 that are responsible for 80% of the benefit, the old 80-20 rule, right? And
Mhm.
so you're looking at a fairly limited number of genes that will, if you correct their expression, so they either under or overexpress, because you get both directions, or misexpress, will result in you being literally physiologically younger. And so you will live longer. Of course you will. I mean, there's a number of genes that people have been floating around. And I think part of the early focus in lifespan extension, which is pretty much past. I mean, everybody's pretty much proved past this, was that everybody was searching for the gene that would give you great lifespan extension. But when you go into animal models, and most of the animal models in lifespan extension are mice, zebrafish, or fruit flies, for whatever reason, we really understand the genetics of those three animals really well. Um, I don't really lay much credence into fruit fly life extension, just saying. But zebrafish and mice, I think, are probably quite relevant. And but most of the ones you correct when you do single gene corrections, you get a 10 or a 15, or if you're lucky, a 20% increase in lifespan, which is
Mhm.
great. I'm not sneering at a 20% increase in lifespan. I mean, you're talking an added 15 years or 16 years. That's a lot. But when you're talking about kind of that, can we get to 200 years or 400-year lifespans, which I think is doable, you need to be stacking corrections in things that affect lifespan. And we have that technology now. I mean, everybody I know in the gene correction space, rather than gene therapy space, is doing it to treat diseases, me included. But we all end up being at the point where, if we can fix this disease or that disease, well, then we can fix these genes that address this other thing called aging. And we're there. I mean, we have that technology now. And then, I mean, the technology that Wyvern uses does it one way. There's half a dozen other ways that people are doing that do the same thing. It's the outcome that matters, not the method to the outcome. And we can do that quite comfortably now. I mean, we have patent coverage on about, well, it's over 80 gene targets now. Um, Composition patents on ways to fix, like, literally over 80 gene targets now, and increasing. So we can do whatever pretty much you want as an industry. I mean, not just Wyvern, other people as well. And so when you've got that capability, then you start saying, well, yeah, I could correct two or three or four very easily and probably get a 30 or 40 or 50% increase in lifespan without really, breaking a sweat, if you want to think of it in a sporting analogy. And I think that's just the case. That's where we are. And, we have, you know, and a number of our patents that we have are the lifespan extension targets. They're not health span extension targets. I mean, we have, like telomerase isomerase. We have one of the components, the TET. component of telomere isomerase. We have a composition of matter patent in the United States on expressing that. And. I mean, there's a whole list of them, and we're increasing more and more of that. And it's here, it's now, and it's just um, basically putting them together and running a clinical study with more than one gene vector and more than one target, and that's coming soon. It might be in Wyvern or it might be one of our colleague companies gets there first, but we're all moving towards that now. And you know, and it is personal. It's amazing how your focus changes to things that matter to you at some point. And yes, I'm turning 70 soon. It hasn't been lost on me that if I'm going to extend my lifespan, I better get around and do it, like RFN. Get going, get going on it, Brad. And so here we are. But I've spent much of my life either being directly involved with gene therapy or adjacent to gene therapy, developing the techniques to make gene therapy products. I mean, we were making plasmids back in the early 80s at quantities that are still much higher than the commercial quantities that you can get now on the yield side. And I mean, high density bioreactors for both animal cells, human cells, and microbial cells at multi 10,000 liter scales and all those other sorts of things. All the things that people use now for gene therapy manufacturing, we were doing 45 years ago. And so, I mean, it's time. It's time for us to actually dip our toe in the water and actually do this. And, I
I-
think we have the
I'm curious.
environment.
I'm curious, Brad. Uh, I would love to understand your process without going into your proprietary information, but I would like to understand more what gene therapy, the sequence or what gene therapy is all about. And I'm also curious to, if I understand correctly, you're analyzing, let's say, 80 genes. Would you, or maybe not, and I'll get the answer now, but but I'm wondering if you're correcting if you have 20 genes that are not are need correction, would you do all of them at once, or would you cure cancer, diabetes, and longevity in the same shot? Is this how you envision things?
Well, I mean, people often ask the question, well, if I cured cancer, like if you could just fix cancer, what would that do to longevity in the total population? And the answer is it doesn't add as much as you think. It's probably 4 or 5 years to the median lifespan, which is still worth it doing. But for the 6 or 7 or 9 million, depending on who you're talking to, people who get cancer every year in the world, it's more like 20 years, right? And so that's why you get that. And cancer is mostly a disease of the elderly. And so that's why it matters. That's why you get that increase in median. But I mean, if you go after a number of these kind of chronic illnesses, that have shortened lifespans, of course you're going to get an increase in median lifespan, like rheumatoid arthritis. Everybody thinks of rheumatoid arthritis as just being something that's pretty much treatable now, and thank goodness it is. I mean, you fix the TNF, you downregulate the TNF that gets into the joint, and you upregulate CTLA4, which is a checkpoint molecule, because it's deficient in RA, and that's why you get autoimmune responses, is because your tissue doesn't have protection. So you fix those two things, and symptomatically RA pretty much goes away. It's a huge advance. And I grew up with enough people that had RA that wasn't treatable when I grew up to know what a huge difference that's made. But even with the new advances, your lifespan is, I don't know, 10 or 15 years less on expectation than it would be if you didn't, because it doesn't completely fix it. So if we could fix RA, how many people have RA? It's like 1 million or something like that you're adding 15 years life to. That That's important. I mean, but you go through all these chronic diseases and you get the same kind of answer. And so, of course, that's going to make a difference. If you can fix type 1 diabetes, that's 100,000 people who are going to live longer. If you fix type 2 diabetes, that's 3 billion people who are that sadly that were either pre-type 2 diabetic or type 2 diabetic now that are going to live longer. And you all of a sudden, by curing diseases, net result in an increase in the population age. But I don't think you push it past the kind of mid to late 80s kind of median without fixing things that don't necessarily cause disease, but just result in aging, like telomere length. Or there's a couple of the checkpoint molecules that don't really matter from an immune perspective, but they matter from a lifespan they obviously matter somehow. And there's a whole host of those targets that you can't really tie to a disease, but they do affect lifespan. Those are the ones I think that we need to fix to get you from the mid 80s up to the, ideally 200 would be kind of my minimum goal. And and then you're going to get people choosing not to live that long because, I mean, really, I mean, life gets pretty repetitive after a certain age, and I think people just lose the will to live. And I understand that. I mean, and I mean, that's actually the most current theory in why time seems to fly faster or move faster when you're older isn't so much that your sense of time uh, compresses, it's that your brain, when you're experiencing something new, is in the moment, and you live every moment through that experience. But on your 45th, 100th repetition of the same thing, your brain just kind of skips over it and isn't really, and you lose the time. Basically, you just skip from the beginning to the end because it's the same. And so I think what the ideal thing would be is for people to reach the time span or lifespan where they just had had enough and that nature wasn't killing them. They just decided enough already and they went off of their therapies and they just progressed and died. That would be, so that becomes your choice rather than the inevitability. That would be wonderful. I know that sounds really science fiction-y, but I mean that's it's within our grasp. We could do it. We could do it now, and um, that's a big change even in over 10 years ago. And it's I mean gene therapy basically when you dig down underneath of it, and it doesn't again like I said, it doesn't matter what technique you use. You're either upregulating something hopefully the wild type version, the native version that your body doesn't make anymore. It either doesn't make it at all, or it's making it misexpresses and it makes something different that doesn't work as well. Or and you see that in a lot of like the muscular dystrophies, the ones that they're all related to each muscular dystrophy has a different protein usually associated with it, and you either make too much or too little of it. And but the ones that make too little of it, it's not they make the same amount of protein, but it's a dysfunctional protein. But basically one side you're upregulating the original wild type version because why would you not go for the best functional version no matter what you do? Like we've got a gene vector that makes insulin, you know,
Mm.
expresses native insulin. Well, that's great. We've also got a gene vector that downregulates some of the things that are associated with diabetes, because diabetes is an autoimmune disease. So some of the cytokines that are overexpressed. So we have gene vectors that downregulate those. So, we can go either direction. But the other direction in gene therapy is to downregulate something you're making too much of. And therapeutically, you think of things like oncogenes. Oncogenes are making too much of, um, EGFR or whatever the oncogene is. And so you downregulate it, and you make less of it, and that restores the homeostasis. But that's really all gene therapy is So when you look at them, they're either up or down. That's really all they are. And with our, I mean, the particular technology we use, which is plasmid based, basically you're coding for either the whatever is too low, so you're coding for insulin, or you're coding for whatever you're missing. Um, and we have quite a few of those. Or the opposite is that you're down regulating, and the way we do it is using either siRNA sequences or miRNA sequences, and I prefer miRNAs, and which are just short. I mean, we use 21 MERS, which 21 units nucleotide, and some people use 19s, and of course you get in these arguments. Well, what's better? Neither of us are right. They have different advantages or disadvantages, but it doesn't prevent you from arguing about it. Um, but that's just our way of doing it. The other people, they use naked siRNAs. Like there's a couple of really good companies out there that have gotten naked siRNAs approved, but all they're doing is down regulating a gene. They're just doing gene therapy a slightly different way than I'm doing, but the outcome is the same. You see people upregulating genes differently than we do, like the mRNA companies. That's what they're doing is they're upregulating something with a naked piece of mRNA. Yep, great, it works just fine. And we just do it differently. That's all. And they're all valid, but the outcomes are the same, up or down. That's it. That's really all you're doing. And it's quite powerful because you know what the native levels are. The first patent that we ever got was for down-regulating TNF, tumor necrosis factor, which is a factor in like Crohn's and IBD, all the IBD family of drugs or diseases, and things like rheumatoid arthritis. We have too much TNF in the joint, and that causes inflammation that you don't want. But you do need TNF. TNF, you don't want to turn it completely off. So what we did is we just built a gene vector that down regulates the production of TNF and in the cells that make it normally. And so they just make a lot less of it. And so you're just measuring it's this high normally, or not normally, but in these abnormal cases, and this is the normal level. You're just reducing it to the normal level. So you're just basically taking it to where it used to be. But that's the same thing you're doing when you're talking about aging, is that, if you're looking at telomere length, which again, is the grandfather, that's what everybody focused on first. And, as you age, your telomere lengths get less because with division, and you don't have your telomere isomerase, which is adding on to it, is not functioning properly. So, and when it gets to a certain length, then the cells can't divide anymore because the chromosomes can't divide. And then you have all these senescent cell populations building up, and that's what limits your age with that particular thing. All you're doing to fix that, and people have done this a variety of different ways, we're not first by any stretch of the imagination in this area, is to just restore telomere isomerase function and to what it was when you were 20 or 25 or whatever. And guess what? Your telomeres lengthen out. And the cell populations that you've managed to do that in live longer. And most of it's people usually treat blood fractions first. So basically you have a young blood system floating around in an older person. And that has health benefits. Of course it does. It's and lifespan benefits. So it's really simple when you think about just up or down. And it's just a different technique to do it. And I have no affection for my technique over other people's techniques because if you get the right outcome, it doesn't matter. It really doesn't matter. So lots of people could do this. It's just the mindset of saying, let's focus on the genes that increase lifespan and realize it's not one. You're going to have to get dramatic increases in lifespan, you're going to have to correct more than one. And so we'll start out with two. And that's our plan. I mean, we've designed a clinical study to fix two. And we're going to, just because I'm a science nerd, we're going to do one that you have to upregulate and one that you have to downregulate, just because then you'll be showing both directions in the same patients. But if you fix two that give you 15 or 20% as individual in animals, then lifespan, then you're going to probably see 30% plus just from correcting two genes. That's a remarkable medical advance. And then you start stacking on more of them after that. I mean, we're, and once you figure out which ones work best, you just keep stacking them. But we should be able to treat patients um, uh, with the technology that we're using in Wyvern. We figure on a per time basis, you're probably maxing out around between 50 and 60 genes correcting with one treatment. So
50
that's
to 60?
yeah, that's a lot of genes to correct with one thing.
It's
And
amazing. So correcting 50 to 60, what do you think would be the result from that correction? I guess you would obviously correct many illnesses and also uh, increase your lifespan. But what is your projection from correcting 50 to 60 genes? Because it sounds a lot.
well, the thing with most chronic illnesses and viral and bacterial infections is that you rarely get over four genes that you have to fix
Yeah.
the problem.
You mentioned about that about cancer.
It's yeah, four cancer is kind of the outlier. It's four, but it's usually one or two, you know. And so, um, you know, I mean, our we've talked about this before. I mean, our
Yeah.
feeling is that someday medicine is going to be you don't feel well, you go down the street to your local gene expression testing clinic, and
Yes.
they do a sample, and 2 days later they phone you up and say, "Yeah, we've made you an appointment with the gene correction clinic, which is probably a different clinic than them down the street, and you've got three genes that need fixing, and they'll do that for you." That's medicine for 90% of the time, including viral and bacterial infections. Um,
Yeah.
because I mean, viral, literally you could shut down any viral infection by playing around with a very small number of genes. Bacterial, we're not as far advanced, so I think it's probably going to be two, but maybe three. And But I'm not certain about that. But it's like malaria. I'm not a bacterial or viral thing. Turns out there's one kinase that if you block that kinase, um, and kinases are just enzymes that add phosphates or take off phosphates. I mean, there's thousands of them. They all do basically the same thing. But this one kinase, if you block that one kinase, then the malaria parasite can't proceed to the next form because they have what, three, four forms that they go through in their reproductive cycle, and a couple are in mosquito and a couple are in human. But if you block that kinase, it doesn't matter whether it's in mosquito or in human, it just stops. They can't go to the next step of reproduction. Well, it's one thing, and you've just fixed malaria because that's a prophylactic, the best prophylactic possible, and it's also the best therapeutic possible. So basically, somebody's got the early stages of malaria, you just that on them, they're done. They go home. That's malaria therapy. I mean, oops, okay, that's pretty cool. But again, that's on the infection side. So, but if you've got the capability of doing 70 or 80 at a time, then you basically, I mean, the only time you'd be doing that many would be if you were looking at health span and you wanted to make a person healthier in 70 or 80 ways. Or cosmetically, you wanted to fix, not just collagen and elastin. You also wanted to, you know, um, do whatever, grow eyebrows if you were losing eyebrows, and you could do that at the same time. And
Or teeth.
or teeth. Well, teeth, I mean, there's a couple of clinical studies in phase twos right now for regrowing teeth. That is, to me, that is like just the edgiest, most wonderful thing possible. I mean, really, I mean, they would completely change dentistry for one thing. But and but so you have different categories in there. But if you were focusing on longevity, you'd say, well, yeah, we want to correct. We've done a gene expression analysis on this patient, and we'll do these 20 or 25, and we'll double his lifespan or triple his lifespan or her lifespan. And you know, all in one shot. Yeah, they're done. See in a year and a half, because with our technology, it lasts about a year and a half. If you're doing permanent changes, like if you're doing, well,
Oh,
lentivirus doesn't, it's not permanent, but it's 5 or 6 years. Or if CRISPR-based stuff, if you want to actually fix the mutations, if we ever fix CRISPR, which we will, 3 or 4 or 5 years from now, the problems with CRISPR will be in the past, which is great. Um, um, so I mean, you could do permanent changes, or you could do temporary changes like what we do, or whatever. But you could mix and match and just pick what you want, or what you could afford, because that'll be what it is. If you can do a lifetime fix to triple a person's lifespan, it's not going to be cheap. I can tell you that. But if you have to treat somebody every year, it'll be a lot less expensive. I mean, that's just gets into healthcare economics. But we can do it. We can do it now. That's the important thing, is that this isn't some sort of science fiction in the 22nd century. We're hoping to do it. We can do it now. And we just have to, one of us is going to do that clinical study to demonstrate that in the very near future. And it might be Wyvern, or it might be one of my colleague companies, but somebody's going to do it. And it'll be, those studies will start this decade, for certain.
mm.
And that's, this decade is, it's not like fusion where it's always 50 years in the future. It's it's like it's now, you know.
We often hear about mitochondrial dysfunction as a hallmark of aging. Uh, how does gene correction or other approaches address the health and efficiency of our mitochondria, which are essentially the powerhouse of our cells?
Well, I mean, mitochondria are the basically degenerate um, progeny of ancestral bacteria that were engulfed by ancestral eukaryotic cells trying to get a good meal, or having a parasite move in that just didn't get eaten or didn't turn into a parasite. I mean, it was about, what, 350 million years ago or something like that. Uh, a eukaryotic cell was floating along and engulfed a bacteria, and the bacteria didn't die or didn't go away and became a symbiote. And so that's what that is. That's what a mitochondria is. It's the descendant of that ancestral bacteria. And so its genome is very bacterial. It still has a plasmid, a bacterial plasmid. It's still whatever, but they get mutations too, and they get dysfunctional too. And there's a number of really good companies out there that are looking at mitochondrial transplants, which I'm very excited about. Um, but we could just as easily fix the genome in a mitochondria using some version of gene therapy. Um, the question is, how do you get the genetic material into the mitochondria? But that's doable. You just have to think a little differently. And people have done that too. So whether you replace the mitochondria with new ones, which people are doing right now, it's amazing, or fix the existing genetic defects in the mitochondria, that's doable now too. But I think it has a significant impact on, there's all sorts of diseases that it's directly associated with. Some of the pediatric Parkinson's diseases are specifically mitochondrial dysfunction. That's it. That's the cause of it. I mean, Parkinson's really isn't one disease. It's probably a dozen different diseases that have the same symptoms. So we call them Parkinson's disease. But that one form of Parkinson's disease is clearly mitochondrial dysfunction. Fix it, you'll fix the Parkinson's disease. But there's a lot of, a lot of aging, like general aging processes are tied to aging mitochondria, basically. And so fix the mitochondria and you're going to make a big difference. I think it's a very important area. And fortunately, there's probably a half a dozen companies that I know, and 20 or 30 that I don't have any awareness of, that are working on mitochondrial repair, basically, if you want to think of it that way. It's a very specialized sub area, and but there's some really good people working on it, like some just like, wow, good people working on that.
In a recent conversation with Dr. Alma Barranco Mendoza, true pioneer in AI for life sciences and co-founder of Infogenetica Solutions, we delve into the science of aging from a cellular and nutritional perspective. She highlighted how a balanced spectrum of fatty acids is absolutely critical for healthy cellular function throughout our lives, impacting everything from brain health and memory to cardiovascular function and even the appearance of our skin. Dr. Mendoza explained that conditions often associated with aging, like Alzheimer and cognitive decline, can be linked to a deficit of these essential fatty acids, even referring to Alzheimer's as diabetes type 3 due to the presence of sugar crystals in the brain. Her product, Neuroactive Oil, is designed to provide these full spectrum fatty acids to support healthy aging by optimizing cellular regeneration, improving sleep, and protecting neural connection. Given Dr. Mendoza's insight into optimizing cellular health through nutrition, how does gene therapy complement or intersect with these foundational biological needs to further enhance healthy aging and potentially extend longevity by addressing root causes?
Well, I mean, the whole kind of nutritional supplement field uh, is dominated by the thinking that things change as you age, really, when you get down to it. And when you see things, it's usually making up for the changes trying via external supplementation. It's basically taking and you're taking what has changed and trying to restore it back to the way it was just externally. It's just a different, basically, mechanism of doing what we do. I mean, for example, your fatty acid profile changes as you age. And it's your normal diet. If you just take somebody and give them a normal broad spectrum fatty diet, and with the same phospholipids, which is where you get your external fatty acids from, your body has to synthesize the kind of odd ones, rare ones, the ones that aren't in that diet. And as you age, that spectrum changes. It does. For example, people often remark that people at age, they smell different. Well, that smell is the result of the fatty acid profile in your sebum that's being excreted on your skin supports a different microflora. It supports a different bacteria, and it's the bacteria that have the different smell. So basically, you're changing the smell component as you age. That's just a reflection of that. And so one always assumes that the fatty acid profile that you had when you were 16 to 20 is the optimum, because it is. And when you're my age, it's going to be different. So to actually have somebody go out, analyze that, and basically force that balance back to where it was nutritionally, it's just a different methodology to get to the same outcome that we do with gene therapy. So I mean, they're entirely complementary. I mean, I could tweak with the fatty acid synthesis enzymes using a gene therapy and force it back to the same balance. The question is what's easier, what's more cost effective, and what's easier for the patient or the person. And I would expect in that case, doing it nutritionally would be easier, more cost effective, than doing it my way. So yeah, that would be great doing it that way. But you can do that with, I mean, there's some things you can do that with, and fatty acids are one thing you can do that with. Lipids as a whole, generally, you can do that with. So there's some of the sphingolipids that you have in your nervous system that you just don't get any other way than synthesizing them themselves. I mean, you have unique lipids that you can't change dietarily. I mean, it's just not possible. So if you needed to fix those, you'd have to do that with gene correction. Um, but there's so many of the things that you can get just out of your diet that can address deficiencies that result because of age. I mean, there's just all sorts of things like, and some of them are you have that complex balance between your microbiome and you. And it supplies a lot of things like vitamin K2, for example. I mean, you produce your own vitamin K2 when you're younger, enough of it. When you get older, you don't generally. Not everybody, but some people don't because your biome changes. So you could supplement K2, which people do, me included, just by taking a pill every day. I mean, that's easy. Or I could genetically engineer your biome, but I don't want to do that. That's complicated and unnecessary in that case. So I'm delighted that people like her are doing what she's doing because I think it really is it's the same thing and it fits. We fill different niches of different needs with the same outcomes. So we're kind of working together, I would think.
Do you think that by restoring our perfect genes, our body will get younger? Uh,
Absolutely. If I fix the elastin in my face and the collagen in my face, it wouldn't look like this. It would be younger, guaranteed. I could easily take 20 or 30 years off the appearance of my face without, I don't think, stretching the imagination at all. Um, but if you restore your, you know, let's just take a bone thing. If we take the osteocytes and get them back to where they were when you were 20, you're going to have 20-year-old bones in 18 months,
mm,
period. You are. If we reset your stem cells in your bone marrow back to where it were in 20 years, it's not going to be overnight. But by the time you get complete turnover of your immune system, you're going to have a 20-year-old immune system in probably less than 18 months, probably 9 months. I mean, it just depends on the tissue because turnover is at different rates. Um, heart muscle for forever has been thought to be the least stem cellish tissue in the body, but there are stem cells in your heart and they do correct themselves. So if you can activate the stem cells back to, I mean, I think children get heart attacks as much as often as most adults do. We just don't notice it because their hearts repair themselves when they're 6. Those little micro heart attacks that cause so much of the heart damage that you don't really notice, they don't have any evidence of heart damage. I don't. So, um, if we could restore your your cardiac stem cells back to basically when you're under 5, yeah, it might take a few years, but once the turnover happens, you're going to have a young heart again. It's just the result of that turnover, and you have to allow the time for the turnover. But once you get the turnover and the replacement, like if you get rid of all the senescent cells in your body, of course you're going to be younger. I mean that, and there's a lot of attention paid to getting rid of senescent cells for that very reason. I mean, basically, my body has a big component of garbage cells. Get rid of those garbage cells, and yeah, you're going to be younger. I mean, you just are. It's I think there's no question we can turn back time. We might be able to not be able to do it with all tissues. Like ligaments might take longer for us to figure out how to do, and tendons, and some of the connective tissue stuff that has really long turnover times. That might be a little more difficult, but things like, I mean, skin, the turnover time in skin is like zero. I mean, it's unbelievable how fast your skin, your dermis, your epidermis reproduces, and the dendritic cells are right underneath there. I mean, it's the biggest immune organ in your body is your skin, which people tend to forget, which is why when you get a sunburn, you're immunosuppressed. Uh, yeah, I mean, I mean, you've got this layer of dendritic cells covering your entire body right underneath the epidermis. Um, and it's the regeneration time, or in your bowel. I mean, the regeneration time, I mean, the turnover time in your bowel layers is days. Total, or your lung, like all your mucosal surfaces, the turnover time's insane. It's so fast. Whereas heart, neural tissue, it's a lot slower. Um, uh, fortunately, we do get turnover in neural tissue. And there's only a half a dozen important growth factors that you need to worry about. And we understand what those are now. And uh, I'm fully expecting things like traumatic brain injuries to be a nuisance injury in the not too distant future because we're just going to be able to fix it, which will be wonderful. And having suffered my share of traumatic brain injuries, I'd be happy to have that happen. So, it, um, yeah, it's just it. The only time I wish I was younger, other than not wanting to die, is when I'm talking about this stuff. I really wish I was 20 and at this stage of technology development because it would be just looking ahead to having that half a century in front of me of being able to work in this area would be great.
Mm.
But that is another reason to want to extend my life because then I can keep working in this area. So that'll be fun.
Well, I'm sure if you collaborate with your peers and invest in the area such as yourself, you can really accelerate that development, if you put all
Yeah.
your greatest mind together.
There's something somebody's pointed out is that a disturbingly large percentage of people that work in our industry end up being on their own clinical studies,
I mean, for sure.
either officially or unofficially. I mean, and the one everybody always points to is that, Craig Ventnor, when they did the first sequencing of the human genome, he was sequencing his genome. I mean, he didn't tell anybody that, but he was patient zero for the Human Genome Project.
Well,
Um,
I got a question about that actually. What do you think about what scientists call junk DNA? Because they sequence our genome, but there's a lot of it that they claim to be junk DNA and not useful. So, any thoughts on that?
what I've observed over the years is that a lot of what originally was thought to be junk DNA, they found functions for. Like some of the siRNA, because your body uses siRNA a lot naturally. Some of those junk DNA sequences were coding for siRNAs, just as an example. There's some of the transposon control elements were in the junk DNA. I mean, so yeah, I think there's junk DNA. I have no question that there's garbage DNA. I mean, our genome is a trash heap of trash heaps. I mean, a third of it's viral. I mean, literally a third of your genome is the result of your one or dozens or thousands or of your ancestors over thousands of generations being infected with one thing or the other and it hanging around and leaving some of itself behind. That's kind of creepy to think about. But well, look at the mitochondria. I mean, literally. I mean, we're a hodgepodge, and you got to know a lot of it doesn't have any function. I mean, it's just there. It's just left over. It'll get edited out. You know, in if we're still around in 10 million years, there'll be a lot less junk DNA in the human genome because genomes are really good at editing out unnecessary things and it's really good at reusing the same thing over and over for different functions too. Um, I mean, look at the organs in the human body. I mean, a lot of them are just jury whatevers, and some of them are just leftover whatevers, like the appendix. The appendix is just the remnant of a rumen, basically, if you want to think of it that way. But your bowel is backwards to like pigs and other caprophages they're and most rumens, because I mean they don't eat, they're really caprophages structurally, but they're not caprophages. Their bowel is inverted to yours. Their rumen is before their digestive tract. Your rumen, your appendix, is after the prime digestive part of your digestive tract. So it's useless. It's of no use to you whatsoever. Um, in caprophages, they actually still have a functional one, like we have the same order as a pig, and they take the contents of that rumen sac and squeeze it out. It's a different form. It comes out the same place, but it's not feces. It's the rumen sac, and they eat it and they re-ingest it and they can digest it. We don't do that. That's good. But um, and that, if you're a pig farmer, everybody that's raised pigs before knows that if you put a pig in a stall where they can't turn around to get it, you have to give them nitrogen supplemented feed to make up for it. That's just the price you pay. So I mean, we're just a hodgepodge. And but yeah, junk DNA. We have to have junk DNA, and it's just how much of it is junk is always the open question, and that'll keep changing because literally, 100. I mean, we've been Homo species for what, 50,000 generations. That's a lot of generations. And at least, I mean, that takes you back to the first use of fire, which is kind of my signature of, it's about 1 million years ago. And it's a lot of time to shed DNA and change DNA, let me tell you. And when you look at all the morphological and physiological changes over that 1 million years, yeah, we've changed a lot. So add another 50,000 years of us pruning unnecessary DNA out and see what we're gonna like, 1 million years from now. We won't be the same, you know. Our descendants will look at us and go, gross. They have teeth.
Yeah.
They have all those toes. Like, why do they have 10 toes? We only have eight toes or 6 toes. And it'll be, uh, wisdom teeth. I mean, that's just a transition from everybody having wisdom teeth to nobody having wisdom teeth, and we're right in the middle of it, genetically, and some people have two, some people have zero, some people have four. I have four wisdom teeth. They're sadly the best teeth I have, but it's just evolution, and that's going to happen to our junk DNA too. The proportion will decrease over time. But you also have to remember that we're continually getting infected with, things like SV40 and HPV and herpes, and they all incorporate, right? And they all leave little bits behind. When they come out, they don't come out the same way. So you're changing before my very eyes.
Mhm. Brad, you operate at the cutting edge of what science deems possible. Throughout history, humans have often sought extreme longevity, sometimes through spiritual practices or anecdotal claims. For instance, I once met a spiritual mystic in India who claimed to be over 304 years old and he stopped counting. Unfortunately, he passed away a couple of years ago. While such claims often fall into the realm of folklore or spiritual belief, from a purely scientific standpoint, with what we know about human biology, gene expression, and the potential for radical intervention, if you had a magic wand and you could create without any limit the longevity and reach what seems to be feasible in the 200 to 400 years. What else in complementary to gene therapy would you use to achieve that objective?
Well, I'm kind of obsessed with gene therapy, which is probably more than obvious by now. But uh,
Yeah.
the I mean, the whole, when you talk about people being extraordinarily old, I mean that pops up through it's all through the Old Testament, and all the original prophets were all hundreds of years old, and 900 years old was a favorite sweet spot. And then you get the Methuselah myths, and you get this and that myth. It's a persistent myth throughout recorded history,
Yes.
and which just keeps getting pushed further and further back because we keep pushing back when we started writing. And you kind of wonder at one point, is there something to it?
Yes.
Are there people out there that live longer? And all you need is to have a a more efficient DNA replication process and a more efficient DNA repair process, and you can cut that mutation rate in half or two-thirds or three-quarters very easily. It's very easy to do with just a couple of changes. It's not complicated to do, and when we do it in microorganisms all the time, just for experiments. I mean, my PhD was on a bacteria that had was hyper efficient at repairing radiation damage, like hyper efficient. Like you couldn't get mutations in it. Like it was crazy. And it was also extremely radiation resistant as a result of that. But why not in a human? Why not have a mutation in a human where a person's DNA repair was just better? Just that's all you take. Or that the DNA replication, because there's only what, three enzymes you need to worry about, that they were just better at what they did. Single mutations, and accidentally you get something that has mutation, and all of a sudden the person lives 150 or 160 or 200. They're not likely to tell people about that. They're not likely to walk around going, I'm old, because people don't respond well to people that are actually 200 years old, I would
Yeah.
expect. So, I mean, that person's going to kind of keep it quiet and just kind of move on and move. People move, and when they didn't have records. So, I would expect that, yeah, there's probably people who've lived much longer than the average. Maybe not 1,000 years, but 150, sure. I'd have no problem with that. And because it's easy to do. And I don't think we can do that nutritionally, candidly. But I think you do have to get down and actually, in this case, you're actually improving the process. You're not just restoring it back to whatever. You're looking for that variant, in this case, DNA repair or variant DNA replication that's improves the function and incorporate that in. And then you're getting into a really ethically dodgy area in gene therapy about it's one thing to restore genetics to when you were 20 or fix a gene error that causes a disease. But when you start getting into the improving on whatever, then you start, little red flags pop up all over the place. Then you start getting serious questions, legitimate questions about what you're doing. The all this, making your lungs be 130% better than the most efficient lung, or making your muscle strength 50 or 60% better, or your twitch response be, twice as fast. People get uncomfortable when you start talking about that kind of stuff. And I don't think there's any question that they have all the right to be uncomfortable about that. But um, so,
Well,
there's
if
also,
we if we push the conversation, I mean, you could potentially even create superhumans. I mean, with
yeah, I think that's very doable. And again, you have to draw a line in the sand and say, you know, my personal line in the sand is I'm happy to restore genes function to the way they were. And if that result of that is that you live a lot longer, great, or you look like you're 20 again, great, or you have 20-year-old functioning, great. I don't have any problem with that. I have a personal line about improving upon the best that nature gave you. It just seems to me an area fraught with problems. Um,
ethics and a bit like cloning.
yeah, those guys that are rumored to be out peddling cloning a brainless clone of you as used as a spare organ thing. I read that the other day and I was like, what are you doing? Like, come on, But if it's possible, people are going to do it. That's the whole thing, is that there's always a percent or two of people in the scientific community that will go there if it's possible. And so you need guidelines and they need to be enforced. I think that's all that we need to kind of go to. I don't
But
have any
somehow
problem.
there's no, since it's such a cutting edge at the moment of where there's no frame around it or no ethics or
No,
I mean
it's like
it's
it's somebody um, maintained a uterus ex vivo now recently. A living, they took a uterus out and they kept the uterus alive and functional apparently. And so all of a sudden artificial womb, and then you get into the Brave New World thing. And I mean, it's I mean, doing uterine transplants, I think is a wonderful thing if that's a possibility for people. But ex vivo uteruses, you start getting into a dodgy area very quickly, you know. And um, I mean, but you're right. When it's new, there's no lines. There's no law saying you can't take a uterus out and stick it into a bottle, keep the uterus alive, and then slap a fetus into it. There's no legal framework for that, you know. So somebody, of course, is going to try it. I mean, of course they will. There is no legal framework for saying
You cannot do
clone,
that.
you clone somebody's just their body and don't bother with their brain, and use it and to harvest organs. There's no legal framework governing that one way or the other. Um, and the chances of you having that conversation with a legislator to get the legal framework before it's a problem is zero. So, I mean, it'll be responsive. It always is. It has to be. So it's going to be interesting because it's going to raise a whole bunch of ethical challenges. And you
So
know,
right now you think you'd have no limitation or no regulatory limitation that would prevent you from realizing your vision because it's there's nothing stopping you basically on
well, I mean, what we're doing isn't going outside the bounds of what you used to be, basically.
yeah.
And that really diminishes a lot of people's concerns. I'm not transplanting parts from one person to another. I'm not creating a life to satisfy another life. Basically, taking a look at a person and just saying, I'm going to restore you back to the way you were. You were, not somebody else. And people don't seem to have a problem with that. They just don't. And I don't, obviously. But I do with some of the other ones. And so I wouldn't go there you know, even if I could, I wouldn't go there. But
But let's assume that our system or our society does not want everybody to live up to 200 to 300 years old because of the way our economy and the whole social system is built. So it's probably there may be some pushbacks to
of
make
course,
that
yeah.
for our
But,
society.
you know, humans seem to be hardwired to want to impose their will on other people. I'll put it that way. It's, you know, the person who literally doesn't desire to have other people do what they want them to do is a very rare creature. And so, of course, somebody, for reasons I may not agree with, will probably do just that. But there'll always be a jurisdiction where that won't be the case. So I'm not too worried about that. I mean, in my
Yes.
case, there'll always be a place. Usually when you talk about lifespan extension, people talk about it only being accessible by the wealthy.
Yes.
And that's the objection to it. And that may or may not be legitimate, but it is an objection and it's very common. So if you say to somebody, well, what if lifespan extension was affordable by everyone?
Yes.
Then most people go, okay, cool. Yeah, that'd be nice. As long as you don't force it on people, because that's the other thing is that some people don't want to live longer. Good for them. They've lived
Yeah,
their
for
life,
sure.
and that gets back to what we were talking about earlier about in my mind, it'd be nice for people to die when they wanted to die, not when Mother Nature wanted them to die. But and that would be the case. But you could say, no, I just want to die when I was supposed to die, originally. That should be your right, in my view. So if you take away the coercion to live longer, which is the mirror image of the not ability to live longer, and also make it so that you generally can make it accessible to anybody who wants it, which
Yeah.
just means you have to make it cheap, which we can do. I mean, making things less expensive is the easiest thing you can do for virtually everything. Doesn't matter what it is. If you just put the time and energy in, you can make something less expensive and with the same quality. It's just a thing that humans are really good at doing for everything. And but you take those two things away, and the number of people that will really object to it are not like in a way. I mean, if I was the general population and my political masters were trying to restrict my ability to live longer, I think many people would object to that. So that might not happen because of that. I mean, who knows? Who knows?
Hmm.
But
Yeah, well, like-
there'll always be a place that you can go to get longevity if
on a Virgin Island somewhere.
or maybe Alberta will be the place. I mean,
Oh, that'd be
yeah,
great.
you know, when
I've another,
when Alberta and Quebec are independent countries, and
yeah.
we're all really, really happy about that. And I'm exposing something here. I'm exposing my beliefs at the moment. Um,
Oh
I
my God.
yeah,
I
I
think gene therapy will be accessible to everybody before we become independent, probably.
oh no, Canada is going to be the same way it is now for the next gazillion years. So yes, if you want a different thing, then you just move somewhere else. That's the easiest thing to do. Um,
I got another Star Trek question for you. The concept of med beds sometimes comes up in discussions about advanced health technologies. From a scientific perspective, is there any intersection between the capabilities of gene therapy and what people imagine with such futuristic healing technologies such as med beds?
oh, absolutely. I mean, again, somebody comes in, they're not feeling well, they lie down in the tube, whatever we call it, and um, uh, auto docs, med beds. I mean, science fiction's got everybody has their own name for it, right?
Yeah,
Uh,
yeah.
and uh, and they lie in the med bed, and the med bed takes samples and
Yes.
gives you a sedative and puts you to sleep just because it's easier to have you lie there. And presumably, I mean, the difference between 3-day analysis and 1 hour analysis is just a matter of spending the money and the time to get it down to that. So yeah, the med bed takes a sample, you're lying at it. In less than an hour, it's already diagnosed everything that's wrong with you genetically and then treats you. Sure.
Yes.
And that's the doctor's office, basically. You know, yeah. Or you
Exactly.
have it in your house, everybody has their own med bed in their basement. I mean, and you go and sleep in there twice a week and it fixes everything on an ongoing basis. I think we have that technology within our grasp now. This isn't, like not hundreds of years from now. You could probably have a functional med bed like that in 20 or 30 years at most. And AI is going to make a big difference in that, candidly. I mean, really, the ability to digest that information and direct the flow going forward in real
Yes.
time is only doable with an AI. And it's just too much for a human to do it in real time like that. And so, I mean, you marry the AI technology that we're sitting on right now with some slightly more speedy testing technology plus existing therapeutic concepts, whether they're advanced biologics or gene therapies or whatever. So that's probably a cocktail of the above. And there, you've got it. And that's in your and my lifetimes without extending them. So that's very cool. That's a very neat concept. And I mean, I don't have enough content knowledge to actually be involved with that stuff directly. So I'll do my little piece on the gene therapy side, and hopefully somebody piece it together on the other part. There's some smart people working in the AI stuff right now. It's just I love dealing with the people that are working on the medical applications of AI because
Yes.
they're just breathtakingly smart and fun to be around. There are no barriers. Everything is possible to them, and they just dive at it. And I love that. It's
Love
wonderful.
that. Yeah. It's amazing. Thank you. So, Brad, this has been absolutely mind-bending and incredibly optimistic conversation. To recap some of the profound points we've covered today, we explored the fundamental question of what aging is at the genetic and cellular level, understanding the roles of somatic mutations, telomeres, and mitochondria, and the crucial impact of epigenetic changes. We delve into how gene therapy works and its potential to reverse or halt aging by addressing root causes, distinguishing between lifespan and health span, and how potentially also other complements like nutritional strategies, like those highlighted by Dr. Alma Baranco Mendoza, and natural compounds help with aging or reverse aging. I'm sorry. We also contrasted this patient-centric approach with traditional one-size-fits-all pharma as the traditional industry. And we discussed the crucial interplay of gene correction with lifestyle, painting a comprehensive picture of the future of health and longevity. For me, the most powerful takeaway is your wavering conviction that we possess the scientific and technological capabilities to fundamentally alter our health trajectory, moving towards a future where living longer, healthier, and more vibrant lives is not a dream, but a medical reality within reach. Brad, for our listeners who want to learn more about your groundbreaking work at Wyvern Pharmaceuticals or connect with you and follow your journey in gene correction and longevity, where's the best place to find you?
Um, Google me on the internet and you can stalk my contact details in just a few seconds. It's sad that that's the world we live in today. It's not hard to track me down, but no, just I mean our website's www.wyvernpharma.com, and that's got an info at contact thing, and I look at that thing every day. So if somebody wants to get a hold of me, they can get same day getting a hold of me that way.
Fantastic. We'll have all those links in our show notes. And for those interested in exploring how AI solutions can drive efficiency and accelerate growth in their own biopharma ventures, you can find more information about WATSNEX Biopharma and how we help visionary biopharma and medtech executives achieve ambitious objectives and overcome critical pains through AI-driven solutions at our website, watsnexbiopharma.com, WATSNEX biopharma.com. If you found this episode valuable, please subscribe, leave us a review, and share it with someone who needs to hear this message. Your support helps us bring more incredible stories and insights to you. Brad, thank you again for sharing your expertise, your passion, and your remarkable insight with us today. It's been an absolute privilege to explore the science of forever with you.
Well, thank you very much for the opportunity for me to bubble the way I usually do when I talk about this particular topic.
Thank you. And to our listeners, thank you for joining us on the What's Next podcast. Until next time, keep innovating, keep questioning, and remember that the future of growth is being built by those who embrace what's next. As Brad might say, stay curious. Thank you.